Okay, as I mentioned before, we're kind of here in the last chapter, last couple of days to go. So we're going to use this time, hopefully, just to kind of knock out the rest of this chapter and kind of all the material, I guess, for the rest of the days here. So we've been talking about kinetics. Obviously, we finished up, not really finished up, but we're kind of in the middle, I guess, of talking about now more specific types of reactions, like first order reactions, second order reactions, and zero order reactions. So as I mentioned earlier, these are kind of the popular orders, I guess, in that sense. They are common orders, and they're really based off of sort of what we've been talking about, how you kind of calculate the rate law, how you calculate the orders and stuff like that. But because, like I mentioned, that most reactions, when you think about ones that you probably have seen before, they have like one reactant, they have two reactants, maybe they have three reactants, but you don't really, again, get, a lot of reactions that have like 4, 5, 6 different reactants going by. So if you just think about a reaction where, you got like A goes to products, or A plus B, or you maybe even in a kind of a rarer case, you don't see too often, three things sort of reacting. If you think about this guy, maybe his order is 0, maybe his order is 1, maybe his order is 2, maybe each of these guys are 1. So you get like a second order reaction, maybe one's 1 and one's 0, first order, one's 1 is, or 2, third order type of thing. Maybe these guys are all first order. You get these sort of third order overall. But in order to get really large ones like, eighth order or 10th order or something like that, where it probably doesn't happen, you need a lot of reactants there to sort of be reacting, and that usually doesn't happen. And so since we sort of usually see it in a lot of cases, one reactant or two reactants, that's why when we talk about sort of typical overall orders of reactions, 0, 1, second order are very common sort of ones that we do come across. Again, just to get sort of a higher overall order of a particular reaction, you would need a lot of reactants reacting at once. And again, that's not a usual situation that occurs. So we've been focusing here on at the end there lecture about first order reactions, which again, you could get with one reactant, that's first order. You could get two reactants where one is first order, one is zero order, and so forth. It has a specific integrated rate law, which is this: natural log of A equals the natural log of A naught minus KT. Again, that's sort of your final concentration. That's sort of your initial. That is your rate constant. And that's your time. In addition, the half-life specific for first order is natural log of 2 over K. And again, this is sort of a graph of the half-life. And again, every half-life, we obviously lose half of what we started with. So if you count the circles, we lost half to there, half to there, half to there. About 10 half-lives or so, you're pretty much done with what you have started with. And remember that, as we've been talking about, the units of the rate constant are really important. So with our first order, reciprocal seconds is typically the units associated with it. Again, it can be some type of unit of time. It doesn't necessarily have to be seconds. Any questions on stuff that we were talking about before? All right, I think we got a couple more examples here. So why don't you take a time here and go over this one. This is first order with the rate constant. What is the, find the concentration of this guy after 865 seconds have gone by when the initial concentration was 0.0225. I'll learn to read, I suppose. So give that a go and see what you come up with. Okay, let's take a look at this. So again, a couple of pieces of information. Obviously, they were nice enough to tell us that it was first order, But if they didn't, we want to look at the units associated with the rate constant. And because they're reciprocal seconds, they just tell us that it is first order. And again, that is important, as we'll see here in just a second, that there are different sort of formulas to use depending on the order of the reaction. And since this is first order, we would want to use our first order equation here, which is the natural log of A is equal to natural log of A naught minus K times T. We obviously do have the K given to us, which is 2.9 times 10 to the minus 4 reciprocal seconds. We want to find sort of the final concentration of this guy. And we do have the time, that's 865 seconds. And we are given the initial concentration of this guy, which is 0.0225 molar. So we do have pretty much everything that we need to sort of put into our formula here. The only thing we're missing, obviously, is the final concentration, which is this guy. So that would give us the natural log of A is equal to our natural log of our initial concentration, 0.0225, minus our rate constant, 2.9 times 10 to the minus 4 reciprocal seconds. And our time here is 865 seconds. So earlier I was talking about units, and here we're okay in terms of units, excuse me. In terms of units here, they're both seconds, but it's very common that sometimes these guys are different units and so forth. So you do want to watch always the time aspect of it, make sure they are in the same units. So in this case, they're both seconds, so we are good to go in terms of that. But again, like I said before, sometimes some are minutes, some are in hours, some are in seconds, and you need to do sort of an additional conversion rather than just plug it in. So always when kinetic sort of deals units of time, you just want to make sure you're careful on those two guys. That pretty much means we have everything we need really to clean up the right-hand side here. So we'll do that. That gives us the natural log of A, which is really our final concentration. We will take the natural log of 0.0225. I probably hit equals, then minus parentheses 2.9 to the minus 4 times 865. That means when we clean up everything on the left-hand side, we end up with minus 4.0450. We'll call it 9. We need to get A by itself, so perhaps you're familiar with. If not, to get rid of the natural log on the left-hand side, you basically need to take E of both sides on your calculator, usually found above the natural log sort of button. So you take the E of this side, and obviously you would take the E of that number there, obviously with the negative. When you do this side, the natural log of the E cancel, and it just leaves you the concentration that's happening. And if you take the E of the other side there, again, making sure you keep that negative, we do end up with 0.0175. The units are going to be molarity from this guy here. And that would be our final concentration. We could kind of make sure it makes sense since it is our final concentration. Since this is a reactant, we expect it to be decreasing with time. We started at 0.0225. We ended at 0.0175. So the concentration did go down. So obviously, if you went up in the concentration, something is definitely wrong. Any questions on first order there or that calculation? Okay, we're then going to talk now about kind of second order reactions and sort of what's going on with those type of reactions. We'll skip this one. It's just a half-life equation. So with second order, it's similar, but a little bit different than sort of first order reactions. So a couple of main things here. Obviously, to get a second order reaction, you could have the common ways are one reactant where it is second order. You could also have, again, two different reactants, A and B, where each of them are first order, which would give you second order overall. So those are two different sort of ways to do it. When we do that, we kind of get a rate law that the rate's equal to K, A to the squared. Again, the two there being second order. If we rearrange and solve for the rate constant and just follow the units, one of the molarities up on top and one on the bottom will cancel. And this leaves us, as we saw sort of earlier, 1 over molar seconds. And these are the typical units that you associate with a second order reaction. Much like first order, again, seconds is a very common unit of time when you're doing kinetics experiments, but it doesn't necessarily have to be seconds. So you could have 1 over, say, molar minutes or 1 over molar hours or days or something like that, and it would still be considered a second order reaction. So again, a lot of times second is, again, your most kind of common unit, but doesn't always have to be the unit of time that you see. Now, there is sort of an integrated rate law for second order, and as you can see, it is significantly different than the integrated rate law that we use for a first order reaction. So for a second order reaction, it's 1 over the final concentration equals 1 over the initial concentration, along with our rate constant and our time. So obviously you can see kind of very different. In addition, being different, we also see a very different sort of half-life equation. The half-life for second order is 1 over the rate constant times the initial concentration. What does that mean? Well, it means that unlike first order, where it's natural log of 2 divided by K, the half-life of a second order reaction is dependent on the initial concentration. Which means, if you just think about it, sort of a larger number there on the bottom is going to give you a smaller half-life or lower half-life than a smaller number on the bottom, right? Just dividing wise, bigger number here, smaller half-life, smaller number, faster half-life. So it is affected by the half-life. Again, if you just kind of do like a 1 over 500 for, say, our initial concentration, gets you 0.002, 1 over, say, 200 per initial concentration, 0.005. And you can see, again, larger number results in a faster sort of half-life, a smaller number, a little longer half-life sort of happening there. So the concentration does obviously make a dependence on this. This integrated rate law, we can also rearrange kind of like what we did with the previous one there on first order, and we get KT plus 1 over A naught. And this is in the form of a straight line, y is equal to mx plus b. And we see that the typical graph that we do for a second order is on the y, 1 over the concentration. On the x is still time. And this will yield us a straight line. The difference between this graph and the previous graph is this straight line actually has a positive slope, which means that the slope will equal k in this case. No negative in this case because it's a positive slope. And again, we do have these sort of important things here. So much like first order, kind of a few really important things to remember. K and the units associated with it for second order, the integrated rate law, the half-life equation, and again, our typical graph that we see here associated as a second order reaction. Now, the last type of order that's very common that we come across is zero order. And it also has its sort of similarities and some differences to the other orders of reaction. In the case of a zero order reaction, probably going to have one reactant where it is zero order. And remember, something to the zero order equals 1. And that's why when we look at the rate law, where the rate is equal to K times A to the 0, basically the rate is equal to the rate constant, which means that the units that we associate with a zero order reaction in terms of the rate constant our molarity over seconds. So for first order, 1/seconds for the rate constant tells you it's a first order reaction. For a second order reaction, 1/molar seconds. And for a zero order reaction, if you have for the rate constant molarity over seconds, tells you that it is zero order. It also has an integrated rate law. It looks exactly like our first order, except there's no natural logs. So again, same guys as everywhere else. This is going to be our final concentration, our initial concentration, our rate constant, our time, and also has a half-life equation where it's the natural log, I'm sorry, not natural log, the initial concentration divided by 2K. So we see here also concentration dependence here on the time of the half-life for a zero order reaction. Much like the other one, we could take this equation and rearrange it a little bit, and it would be solved for a straight line of y is equal to mx plus b. Again, for our zero order, we graph the concentration of A. And again, on our x here is our time, going to yield us a negatively sloped line where the slope is equal to minus k. Now, you may be saying, I think I've seen this graph, and you would be right. We did see this graph of the concentration versus time for a first order. And that is the same two things that are being graphed, but the resulting graph is different. If you graph the concentration versus time and you get a straight line, you're dealing with a zero order reaction. If you graph the concentration versus time and you don't get that straight line, you get that kind of decreasing with timeline, that's going to be a first order. So the actual graph itself is different. And usually when we look at graphs for these sort of kinetics experiments, we usually look at sort of the linear relationship. So this graph is mostly thought of as the zero order graph, and it will yield you a straight line. So our same sort of things when you're dealing with kinetics and dealing with zero order that are important are units of K, the specific one for zero, half-life, and obviously the specific graph there for half-life. I'm sorry, for a zero order. Question on that one there. All right, so I want to take a second here and see what you come up with. We got second order initial concentration after 5 times 10 to the 2 seconds. What is the rate constant? So they do tell us it is second order, and they would need to in this particular case because we are solving for the rate constant. So obviously we don't have the rate constant and the units available to us to let us know what order we're dealing with. So because they told us it's second order, we again obviously want to use the appropriate equation here, which is our second order equation. And if we go through here, we do have our initial concentration, which is 0.01. We are timing at, I call that 500 seconds, I think. And our final concentration here of Q, which ended up at 0.0010. And we're looking for K. So we do have pretty much everything we need to plug in. We just want to make sure we get everybody in the right spot. So this can be 1 over the 0.20 molar. It's equal to 1 over our initial 10. This is plus. And we are looking for the rate constant, and our time here is 500 seconds. Personally, I would take 1 over the left-hand side there, so 1 over 0.0010. Hit equals, then subtract this guy to the other side, which would be 1 divided by 0.01. That's going to give us a 900 over here, which, by the way, is 1 over molar in terms of units, equals K times 500 seconds. We're going to then divide this to the other side. So we'll divide that by 500, and that is going to give us 1.81 over molar seconds as we bring the seconds to the bottom when we divide. And that is the units associated, right, with a second order reaction, as we saw, 1 over molar seconds. Question on that calculation there. So first order, second order, zero order are really common sort of orders for kinetic sort of reactions and kinetics calculations. And this next table sort of summarizes, sort of all of the formulas and stuff that go together. And like I said, these are probably the most common ones. And you definitely will see this again in 200B if you take 200B, because when you talk about radioactivity, all radioactive decay follows first order kinetics. So you use these guys for radioactive decay type problems and so forth. They all follow first order kinetics. So you do see it again next semester. And I don't know these days what goes on there in 200B, but years ago, your final used to have a lot of kinetic sort of information on it. So you might see some of these, but definitely in a specific chapter that you cover, usually in 200B, you will see kind of these guys again used in a sort of radioactive decay sort of situation for sure. In addition to, obviously, you can use any of those guys for normal sort of chemical kinetics type problems. Now, we talked about sort of those graphs, and another very common sort of kinetics experiment that's done is to try to determine really, what the order of a particular reaction is. And one way that you could do that is obviously you could run the experiment, gain all your information, and then really you can do all three of those graphs that we talked about. You can do your, kind of natural log of A versus T, which would be first order. You could do your graph of 1 over A versus T, which would be second order. Or you could do your graph of A versus time, which would be 0 order. And basically, if you were trying to sort of determine experimentally, sort of which graph is which, or which reaction is which, you would basically graph the information, all three of these graphs, and you oftentimes would use some type of program like Excel, and you would look for the R squared value. The R squared value is what is sometimes referred to as the linear coefficient. And it basically, if it is a value of 1, it means you have a perfect linear relationship with your data, which means you basically have a perfect straight line. You would do this and try to find one that of these three graphs that was the closest to 1. And if it was the closest to 1, then you would know that would be the order for your particular reaction. So let's just say, for example, my R squared value here was 0.91, a little wiggly. My R squared value here, oops, R squared on top, value was 0.96. And my R squared value here was 0.99. Made up numbers, by the way. If I did these three graphs for the same information, obviously graphed correctly, that would tell me that my reaction would be 0 order, as this one is the most linearist sort of graph that you got. So again, graphical ways of determining sort of the order of reactions, a very common experimental procedure that's done. And that's why when we talked about sort of first order, second order, 0 order, why it's usually important to obviously understand what the graph should look like, because it's a very common process. Any questions on that there? So now we sort of understand some different orders. And again, as we talked about, sort of, you could use those orders to, if you know the rate law for a particular reaction, the orders that are associated with those guys, you can, as we talked about earlier today, really play with concentrations. If you need to maybe speed up a reaction, you can maybe double one concentration versus the other. If you need to slow down a reaction, you could maybe lower a concentration of one versus the other. And again, that's sort of the practical application of understanding the orders and of a rate law. You could really, kind of play with the reaction, get it to maybe occur at a rate at which you're looking for, and you can really kind of dial in sort of the concentrations that you would need to achieve a certain rate. As earlier, just I made up example, by just doubling one of the reactants, we were able to make the reaction go basically 4 times as fast. Or if we just doubled the other reactant, we were able to make it go twice as fast. And as we talked about before, if you needed to slow it down, maybe you cut a concentration of a reactant by half, and it may affect, slow down the overall rate of the reaction. So, these are sort of the practical benefits of understanding the rate law and the orders and everything that's happening. We're now going to kind of talk about a little bit of how temperature and such affects, obviously, the rate of a particular reaction. And these are 2 energy diagrams that we're looking at here. And when we look at these energy diagrams, a couple of things that you should be aware of. One represents an endothermic process, and one represents an exothermic process. So again, we didn't talk a heck of a lot about energy in this class, but we did touch upon exothermic and endothermic and basically what it means. Remember that something is exothermic, it means that heat and energy is released. And one way that we sort of recognize sort of that aspect of it is by, as we talked a little bit about, delta H, which is the enthalpy. And basically, if we're doing something that is sort of exothermic and giving off energy, usually the value for energy really will be represented by that negative number. So a negative number in terms of delta H, which is the enthalpy, in terms of Q, which is the heat or energy, usually indicates an exothermic reaction. Opposite of that is an endothermic reaction where heat and energy is absorbed. Again, usually displayed with a delta H that is a positive number. So again, when we talk about sort of a positive number, in terms of energy, that usually implies that it's an endothermic reaction coming by. How can we tell the difference between these 2 diagrams? Well, it really results around where we see the reactants. Over here, our reactants versus our products over here. And what we see in this case is our reactants are higher in energy than our products. And the only way for our reactants to get down there in terms of energy to our products is energy has to be given off, which means this is a common exothermic energy diagram. Reactants higher in energy than products means that it's going to net give off energy, and it will be exothermic. The opposite is seen over here, are endothermic. Our reactants are actually lower in energy than our products. And in order for our reactants kind of get up there in terms of energy to our products, we have to put energy in this case, and it needs to be absorbed. And what we see is a couple really important parts in terms of a reaction is there is always a hill that the reactants has to climb to get to the other side. And that hill is from where the reactants are in energy to kind of the peak of the hill. This is what is referred to as the activation energy, the E of A. And the activation energy is the minimum amount of energy that's required for a reaction to take place. Now, sometimes people think all you need is like 2 things basically to collide with each other. And that's not always the case. So basically 2 things has to happen. A, they do need to collide, but they do need to collide in sort of the right location, sort of the active side. And they need to collide with each other with the right amount of energy, which is really the activation energy, to start that chemical reaction. So there is times where collisions occur and no products are made because one of those 2 things are not sort of made. So this hill here is our activation energy. And the hill over here is our activation energy here in our endothermic reaction. Now you also see this little guy up here on top has a little funky symbol on it. And that is what is sometimes referred to as a transition state complex or an activated complex. And that is because the very top of the curve there, that is what is sometimes referred to as a transition state. So what is happening at that point? Well, in order for A and B to make C and D, all of the bonds on A and B need to start breaking, and they need to start making new bonds. So as these guys are kind of crawling up the hill here in terms of energy, we got our reactants that are starting to break bonds. But at the same time, they're starting to make some bonds. So breaking bonds, making bonds. And when we get up to this sort of guy at the very top in terms of energy, we oftentimes have something where we have sort of partially made and broken bonds happening. So we got this sort of transitioning happening, which is why I sometimes refer to as transition state. We're starting to break apart the bonds, but trying to make some of our new bonds along the way. And then usually very fast, it kind of drops down the hill to our products to the other side. Now, what we see here in terms of our transition state and where our transition state complex is it is at very high energy, right? And one thing that you probably should know is things in very high energy are not very stable, right? Things don't really want to be very high in energy. So that's why usually when we get up there at the very top of the hill, it kind of goes down to the other side relatively quickly because it's a very, very high in energy. And really the whole goal of sort of bonding, reacting and stuff like that is to kind of bring down the overall net energy that's sort of happening. That's why transition state complexes are usually very hard to isolate. They're sometimes referred to as intermediates because they don't really hang around a very long time and they kind of drop down to the other side really quickly because they're very high in energy and not very stable. Any questions on that? How does the activation energy really sort of play an effect on the rate of a particular reaction? Well, if we think about the activation energy as really the hill that the reactants have to climb, and we think about just our real life here and hills that we climb, if I'm climbing this hill here versus the activation energy over here, which is this big hill over here, the shorter or the lower the activation energy, the smaller the hill, probably the faster the reactants can get to the other side, then more reactants to have the appropriate amount of energy to get to the other side, which would result in the reaction happening a lot faster, as opposed to here where, you know, there's probably a sligger hill to climb. You know, if you had to go all the way to the top and over, it's going to take you much longer than if you had to climb this hill. The result is this reaction is probably going to be perhaps a little bit slower, but it has a bigger activation energy. Also why it's sort of endothermic, right? To kind of help people get up and over the hill, kind of put some heat and energy in there to get enough people to have the right amount of energy to get up and over that hill. So obviously the larger the activation energy, typically speaking, the slower the reaction would be versus something that has a much smaller activation energy. Any question on that there? So the effect of temperature on the rate of the reaction, as we've talked about, is obviously as we sort of increase the temperature, we typically will see the reaction occur faster. And again, if you just think about what we were just looking at, if we increase the temperature, there's going to be a greater proportion of molecules that have more energy or enough energy to get up and over that hill to the other side. Thus, the reaction would occur a lot faster. Vice versa, if you lower the temperature, you now have kind of removed a lot of energy from those reactants. There's going to be a smaller amount of guys that have enough energy to get up and over to the other side, and thus would result in perhaps a much slower reaction basically occurring in this particular case. This is the Uranus equation, which basically kind of relates temperature to sort of the rate of a reaction. Some of these things are some things that we've seen before. This is our rate constant. That is our activation energy. And by the way, when we do calculate, and we'll look back on this graph here. Whoops. When we do calculate activation energy, E of A is usually a positive number. Again, you can see it's added in each of these cases, and activation energy is usually a positive number. R is our gas constant, but it is the one that involves energy, so that's the 8.314 version of it. And T here, this T is capital T, which is our temperature in Kelvin. A is the frequency factor, and as we'll talk about it, it's sort of the proportion of molecules that really do have the correct amount of energy or enough energy to kind of get up and over to the other side. As you can see here, again, our activation energy and then our products being formed. So again, as these guys are kind of coming up the hill, they're breaking bonds, starting to make bonds, kind of partially made, partially broken bonds, and then down to the other side to make our products in this case. And as I talked about, the energy barrier for most reactions is our activation energy. And again, when we do get to that very top, we have what is referred to as an activated complex or a transition state complex. And again, something that's very high in energy usually doesn't hang around a very long time because of it being very high in energy. And it's because of those kind of partially made and partially broken bonds. It's sort of where we find at the peak of energy where things are starting to break apart and come back together at the same time. Now, here's that graph of a Uranus sort of relationship. And what we see here is what we talked about, the relationship between temperature and the rate constant. And again, you can think of the rate constant as sort of the rate of the reaction. Larger the rate constant, the faster the reaction, kind of the lower the rate constant, the slower the reaction. At a lower temperature, we see a lower rate constant or a slower reaction. As we increase the temperature going this way, we see a significant rise in the sort of rate of that reaction by increasing the temperature. So as we saw earlier, we can sometimes, as mentioned, if you sort of raise the temperature of reaction by like 10 degrees Celsius, you can oftentimes double the rate of the reaction. And again, it's just providing sort of a everybody more energy to kind of get up and over that hill. Now, the Uranus equation, a lot of times people will not use this version of it. They will actually use the natural log version of it, which is what we see here. And going through the top equation, taking the natural log gives us the natural log of K is equal to, and it is minus, I'll make the minus over here, just kind of cross out, minus E of A over R, 1 over the temperature plus the natural log of A. This is basically the formula in a straight line. Y is equal to, let me just rewrite it over here. Natural log of K is equal to minus E of A over R, 1 over T plus the natural log of A. This is Y is equal to MX plus B. So a very typical Uranus plot, as we will see shortly, is on the Y, we graph the natural log of K. On the X, we graph 1 over the temperature in Kelvin. And that will yield us a straight line-ish. And from that straight line, we can actually use it and the slope, because the slope of this line will equal minus E of A over R. R is the gas constant, was 8.314. The slope would obviously be given from the line here in the graph, and we can find the activation energy. Now, because we typically will graph this, and I'm not making a very straight line, but we'll assume the straightish. Because this line has a negative slope, the slope number here would be negative. The negative here will again turn our activation energy into a positive number, which again is what it should be. The other thing that you want to kind of watch out for, in case mathematically speaking, you kind of use this equation, is the units of these guys. R is in joules per Kelvin per mole. Usually activation energy is in kilojoules. So a lot of times unit wise, you do have an issue. You got to do a conversion. Otherwise, you'll be off by a factor of 1,000. And that's, again, a very common mistake sort of mathematically when people sort of use this equation. Again, because R is in joules, your activation energy actually will be joules when you solve for it, but it's typically given to you in kilojoules. Here's a much prettier picture of a plot than the one I drew. And again, the negative is like way out there. Yeah, negative. So this again is our y is equal to mx plus b. Here again, the slope would equal minus e of a over r, which means if you want to graphically find the activation energy would be minus r times the slope. And again, if you do this, though, it will be in joules because this is in joules. We do it graphically, so that's a good thing to remember in terms of units. Now, the other thing that you can actually find from a graph such as this is your frequency factor, which again is that proportion of molecules that have a sufficient amount of energy to get up and over the hill. That is equal to the y-intercept, right? So you most likely would have a formula or an equation given to you if you graph this, but you could go the natural log of a is equal to the y-intercept, and you could solve for a in that case as well by rearranging and solving. So a very common sort of thing is to do a plot such as this to figure out activation energy from the slope. As I mentioned before, again, when we talk about sort of that frequency factor, it really does sort of represent the fraction of molecules that really have sufficient amount of energy to kind of get up and over that side, that hill of activation energy. And as we talked about, increasing the temperature very much helps that, gives everybody enough energy. And again, the opposite of that obviously is if we lower the temperature, we're really removing that energy, and we're going to see a very smaller proportion of molecules that really can get up and over to the other side. As we can kind of see in this graph here, this the blue graph is temperature 1, the red graph line there is temperature 2, and temperature 2 is at a higher temperature than temperature 1. The dotted line represents the activation energy. And if we look at the activation energy up to the lower temperature line, that is the proportion of molecules that have a sufficient amount of energy to get up and over the hill to the other side, really to make products. Now, if we look at the higher temperature at that activation energy, we actually have, I'll go to the right of it down here, this much fraction of molecules that actually now have a sufficient amount of energy to get to the other side. So this graphically shows us that we can increase the amount of molecules and stuff that do have the right amount of energy to get to the other side by increasing the temperature, and vice versa. If we actually started at this temperature, the higher temperature, and ended at the second temperature, we could see that the amount of guys that could get up and over to the other side has decreased significantly. All these things obviously would play an important role and a factor in how fast the chemical reaction would occur. Again, the idea there is if more guys have enough energy to get to the other side, they will get to the other side faster. The resulting is you will see the reaction occur quicker, and vice versa. Obviously, if a smaller proportion has the right amount of energy to get to the other side, not as many will get to the other side, not as much products would be made, and we would consider the reaction to be occurring a lot slower. Any questions on that there? In case you missed it the first 3 times we saw this equation, that's the same equation we've been dealing with. Just to kind of show you sort of, how one would sort of approach a problem like this. This is a typical sort of table that would be given to you in a problem that you would have to do this. You would be given the temperature, and this table is actually a really nice table because a lot of tables that you would be given the temperature, this would actually be degrees Celsius a lot of times. So you would have to first convert it to Kelvin, but they actually did that for you. You also would be given the rate constant at these specific temperatures. And again, you would need to use your Uranus equation there. And do some conversions. So remember that on the y, we're going to plot the natural log of k, which means that here you have just k, which means in all the k column here, you would have to go through and basically get the natural log of k. On the x, this is 1 over the temperature in Kelvin. So they happen to be in Kelvin already. If they weren't, you would have to go from Celsius to Kelvin and then take 1 over the temperature. Once you did all those conversions, you then would do a best fit plot, a linear plot, and you would get a plot such as this. And a plot such as this, and again, if you use Excel or if you did it by hand, I suppose, you could get the equation for the straight line that occurs here. And if we wanted to determine the activation energy and also the frequency factor here, we could do that by, as we saw a second ago, our natural log of k is our minus e of a over r, 1 over t, plus the natural log of a. So y is equal to mx plus b. So the first thing that we could very much easily solve for is the activation energy. It would be the slope of that line, and that is what this number is. That's the slope of the line. We see that the line is a negative slope, which is why it's negative here. So our slope would equal minus e of a over r, which means our activation energy would equal minus r times the slope. So minus r, which is 8.314 joules per Kelvin per mole, times our slope from our guy, which again is negative, 1.12 times 10 to the 4. And again, those two negatives are going to turn our activation energy into a positive number. And we will end up with an activation energy of 93116.8. The units here are really joules, but in most cases, activation energy is given in kilojoules. So if we divide that by 1,000, we end up with 93.1 kilojoules per mole would be our activation energy for this particular reaction based on the information given to us. Any questions on how I got that one there? Now the frequency factor, that is A. And again, that's sort of your proportion of guys that have the sufficient amount of energy. And again, if we go back to sort of our equation here, we see that the natural log of A is equal to the y-intercept. That's what B stands for. The y-intercept is this number here from our equation, and that would be 26.8 is equal to the natural log of A. To get rid of the natural log of A, we need to take E of both sides here. So E of this and E of that there. Again, the natural log of E will cancel out, leaving us just the frequency factor. And if we take the E of that guy, we end up with, we're up there, 4.36 times 10 to the 11. Now, sometimes people go, what are the units of sort of our frequency factor? Well, remember that this is really the y-intercept, right? So it's like the y-intercept over here. And on y is the natural log of k. So if we go back to k, the units are 1 over molar seconds. And that would actually be the same units that we would use here, be 1 over molar seconds. So you may be asking how that happens. Well, when we take the natural log of k, our K started with 1 over molar second. When we take the natural log of K, we actually get rid of the units. And that's what's here, something with no units. But now when we do our calculation to find A, we're taking the E of it, which is getting rid of the natural log and bringing us back really to the units of K, which is 1 over molar second. So the short answer is pretty much if you're asked to calculate sort of the frequency factor, usually I would say in pretty much all cases, it will end up with the same units that are associated with the rate constant. Any questions on that there? All right, so let's take a look here. Now, most of the time we don't want to do graphing when we're doing this stuff. And we oftentimes want to use kind of a 2-point version of it, more of a calculation version than graphing. And you could do that if you have really 2 pieces of information. And this is basically the 2-point version of the Uranus equation. And that's the natural log of K2 divided by K1. These are rate constants at different temperatures. Our E of A is our activation energy. And our R is our gas constant. And these are temperatures for each of the rate constants, and they do need to be in Kelvin. This is definitely the one that I was talking about in terms of energy you got to be careful of. This is typically in kilojoules, and again, our gas constant is typically in joules. That means that, you know, you got to watch that. Otherwise, you will have sort of the wrong value, if you will. You'll be off by that factor of 1,000. So this is a very nice one. If you have kind of 2 pieces of information, you can just mathematically sort of solve for maybe the activation energy, maybe a rate constant, maybe a temperature, without having to do some type of graph. So let's take a look and sort of see how one looks like here. We have a rate constant at 2.57 at a 701 and 567 at 895. So we do see temperature increases. So this is the value of the rate constant. The rate goes up a lot in that case. So we can use our 2-point version here to calculate it, which is K2 over K1 is equal to E of A over R 1 over T1 minus 1 over T2. And if we just kind of pull out our information, we do have our K1 is 2.57 and our temperature is 701 Kelvin. Our K2 is 567 and our T2 is 895 Kelvin. So we always have R as well, which is 8.314 joules per Kelvin per mole. So in this case, the only thing that we're missing is the activation energy. So we can plug our numbers in. So natural log of K2, which is 567 divided by 2.57 is equal to our E of A, which is what we're solving for, 8.314. And our first temperature, which is 701 minus our 895. So if we kind of clean up everything on the left-hand side there, we want to actually divide first and take the natural log of it. And that gives us something like 5.396. It's equal to E of A over 8.314. Kind of clean up what's in our parentheses here. Gets us something like 0.000309. We're going to multiply by 8.314 and then divide that to the other side. That gives us 5.396 times 8.314 divided by 0.000309. Gets us an E of A, or an activation energy of 145,185. Units here are joules because of this guy. 1 divided by 1,000 gets 145 kilojoules is our activation energy. Again, here we do get a positive value for our activation energy. And again, this is a very common way to sort of calculate based off of kind of 2 pieces of information. Any questions on that? Okay, so sorry to finish up this chapter here. We're going to talk about sort of reaction mechanisms. And by the way, when we're done here, we're almost done here with this chapter. We're going to talk about, the final and what you need to know from all this stuff. And it won't be much, I don't think. So here we are talking about mechanisms and sort of how reactions occur. And this illustrates sort of what I was talking about earlier, that, we can get collisions here that do result in products being formed. So like the orange part hits the purple part, and that's sort of the right part for this reaction to occur. But if we kind of collide in the wrong direction, where this kind of carbon hits the orange guy, those going to result in no products being formed. So it's really important. It's really important where things sort of collide, how they come together and the right amount of energy for products to actually be made. So one last thing about kinetics here, which is reaction mechanisms. And we're not going to go very deep into reaction mechanism, but I just want to touch upon a couple of things. First off, reaction mechanisms are ways that you could sort of explain how a particular reaction takes place. Now, sometimes when we look at an overall reaction like A plus B goes to E plus F, we sometimes assume that it all happens in one step. Like it directly goes from reactants to products. And that's not always the case. Sometimes it happens in multiple steps, like A plus B first maybe makes C and D, then C and D react to make E plus F. And if we add both of these steps together, just like we did with redox reactions, anything on opposite sides of the arrows can cancel out. And what's left on the left-hand side is A plus B. What's on the right-hand side is E plus F. And that's our overall reaction. So sometimes it does occur in multiple steps. And we see that, for example, in a reaction such as this. In this reaction, when this occurs, N2O2 is actually detected, but you do not see any N2O2 anywhere in this reaction. And what that implies is, as this reaction is happening, somewhere along the way, N2O2 is made and then has to get used up before the end of the reaction. And that brings us to what I refer to as reaction mechanisms and elementary steps. And elementary steps are the individual steps in a mechanism that leads to products being made. Now, in this particular case, if we did this, we would see that the N2O2 cancels. And if we add this together, we get our 2NO and our O2, which is in our overall reaction, and our 2NO2. This also explains why N2O2 is detected in this reaction. In an earlier step, we make it, but then in the next step, we use it up. So that's why we kind of see it appear, but it gets completely used up. So whenever you're dealing with something that is made early on in a mechanism, but gets used up completely, that's what's referred to as an intermediate. An intermediate is something that kind of comes along early on in a reaction, but really 100% gets used up by the time the reaction's over, is not present at the end of the reaction, which is why you don't see it in the overall reaction. Now, what are reaction mechanisms? Well, there are ways to sort of predict how a reaction occurs. Does it mean in every situation the reaction always occurs the same way? It doesn't. There could be multiple ways a reaction could occur, multiple mechanisms. But when people ask, is this a good mechanism or a bad mechanism? Most of the time people are trying to determine if they say yes, that this is a plausible way this reaction could occur. Again, it doesn't necessarily mean it will always occur in that way, but it was most likely could occur that way. So what about mechanisms and sort of kinetics and rates? Well, usually somewhere in a reaction mechanism, for example, this one's only 2 steps. Maybe there's one is 3 steps, 4 steps, 5 steps. But in this one of these steps, you'll usually have a step which is what is referred to as the slow step. And the slow step in the mechanism is really what is known as the rate determining step. And that is sometimes referred to as the RDS. The rate determining step is really the slowest step in the mechanism. And it is the one that determines how fast the rate's going to occur. So this is the one that really determines how fast the rate of the reaction will occur. It's kind of like when you're in the sort of 5 items or less line and the guy's got 400 items in front of you, you're definitely not getting past that line until he's pretty much done with his sort of shopping. And same idea in the mechanism. Usually there's one step, doesn't have to be the first step, could be the second step, could even be the third step, but there's some step along the way that pretty much is the one that's kind of holding up the show. And the reaction really will not proceed to products until you get past that step. And that again is what is referred to as a rate determining step. Any questions on that? So we're obviously not going to go into deep detail on that or how to do mechanisms. So we'll just jam through this stuff. But let's finish up though, talking about catalysts, which we did touch upon the other day. A catalyst, a reminder of what a catalyst is. A catalyst, again, is not a reactant. And again, it's not a product. And it does not get used up. In the reaction. It is there simply to facilitate that reaction occurring faster. And again, there are negative catalysts, but again, most of the time people are looking at a catalyst that's speeding up a chemical reaction. How does it do it? Well, it sometimes provides a way for everybody to come together in a more efficient fashion. And what that ends up doing is, instead of in the uncatalyzed reaction, having this big hill to climb, we do the same reaction where we add a catalyst, we see that the activation energy lowers, which means the hill is much smaller, which means more guys could get to the other side faster. There'll be a greater proportion of molecules that have enough energy to get to that other side, and they're able to really get to the other side faster, make more products, which thus would increase the rate of the reaction. So how a catalyst works is it finds an alternative pathway, lowers the activation energy, allowing everybody to get to the other side faster, more molecules to get to the other side faster, resulting in faster product formation. Kind of like the old cartoon, right? Like the coyote and the roadrunner, right? It's like going up and over the hill, like the roadrunner opens like the door of the hill and just goes straight through to the other side, gets to the other side faster. The coyote hits his face in the wall, I suppose, but you know, it allows you to get really to the other side a lot quicker. And when we talk about catalysts, they can be 2 different types of catalysts, as we touched upon earlier. They could be heterogeneous, which means that the catalyst and whatever is reacting are in different phases. So for example, maybe you have a metal that you're using as a catalyst. That's a solid, and maybe you're using it with a gas, or maybe you're using it in a reaction that involves aqueous ions. Or it could be homogeneous, which means that they're in the same phase. So maybe you're doing a reaction with solutions, which are aqueous, and you add an acid, which is an aqueous solution to it, and it helps to facilitate the reaction to occur. So here's an example of the Haber process, which is the making of ammonia, but just for our purposes to look at it, this is the catalyst. And again, there's some attraction between the catalyst and what's floating around. So again, it just allows everybody to kind of come in a central location. Also helps with breaking apart some of the bonds as well, and allowing them a nice platform to sort of reform and make the products that are going to occur in a much faster and more efficient manner than, again, if they were just kind of flying around trying to find one another. This is the making of nitric acid, same idea. They use sort of a metal catalyst like platinum, and it helps really speed up the reaction to occur to actually make nitric acid. We also have solid catalysts in our cars, or if you have a catalytic converter, I guess to say that these days, there's electric, I suppose. But again, our catalytic converter, they do have kind of two separate sections. One takes care of some of the carbons, one takes care of some of the nitrogens and those kind of things, and hopefully allows the reaction to occur, that no pollution goes out the tailpipe in your particular car. There's kind of honeycombs in a lot of the catalytic converters that have certain metals in there that help facilitate this reaction to occur, as sort of unburnt hydrocarbons from gas and so forth kind of go through those two different chambers, one to catch one sort of pollutant and one to catch another one, and turn it into something that's sort of non-polluting as much as it would be if those guys were just released. So catalysts can be same sort of phase, catalysts can be other phases, but important thing about a catalyst is ultimately the way most of them work is they lower that activation energy that allows a greater proportion of molecules to get to the other side, and resulting in the reaction occurring a lot faster. And again, they can be solid, and different phases are the same phases, but they typically are not considered a reactant or a product, and they don't get used up. Any questions on catalysts? All right, well, congratulations. That is experiment 11. That is chapter 11.